because the process is more regular, more predictable than you think, we'll double your money. That is, we'll give you 1 bit more in the doubling rate. By the way, these are all base 2. That's why I can say one unit here will double your money. If the logs were base E, all the calculations and maximizations go through, and then a unit, this would be natural log, and a unit here would multiply your money by E. But we're talking about the same analysis. We just have to keep track, make sure it's the same base log in each of the computations. All right, now, so why did I call this an application? Because I was thinking of the past as side information. All right, here's another application. Does anybody have a deck of cards? No. All right. You have a deck of cards?
Sorry. So you're saying
we could take the break early, you see, and play Hold'em. All right.
Anyway, so my question is, you were saying that it's equivalent to either bet like all at once.
Yeah, thank you.
Or to bet as you go.
Yeah.
So if you're betting like all at once, then I can see as time goes, as n goes to infinity, you bet all at once that your W star converges. So it's the same when it's like your effective W star.
Yeah.
Will converge when you're betting as you go, because as you go, your W.
Well, yeah, the problem would. Yeah, see, I want to let n, the number of horse races, go to infinity. So the notion of betting all at once makes a lot of sense for finite n. But then I want to let n go to infinity. Do I bet all at once on the infinite sequence? I can think of it that way. But, right. Does that address your question at least? Good. Okay, here's application 2. Red, black. I'm going to give you, you have to write down here, I'm not going to spell it out here. I'm going to give you even odds on your guessing red or black for the next card. Half of the cards, this is a 52 card deck, are red and half are black. Okay? You have an initial $1. Say if you bet it all on red and you lose the first bet, you have $0 next time and $0 to invest the rest of the way. You're broke. Okay? If you bet half on red and half on black, I'm giving you 2 for 1 fair odds. You get your $1 back because one bet doubles and the other is lost. Okay? So, how much would you bet on red for the first card? Half, half, half. You get your $1 back, and it is black. Good thing you didn't bet all on red. All right, now, the next card, you have some side information. What do you think the color is going to be? The first card was black. You think it's red, right? But you don't think very strongly that it's red. How much do you bet on red? Excuse me?
26 over 51.
26 over 51. Right. So you bet that. It's red. So you bet S0 is 1. S1 is 1. S2 of these outcomes turns out to be 26 over 51 times 2, which is 52 over 51. Congratulations, you've made 2% on your money. All right. Now the next one, it's equal, so you bet equal, it's red, and you continue on, etc. And I heard your algorithm, or implicit, you bet in proportion to the number of cards of that color left. All right. We're down to the last card. Now you know the color of all the other cards. So you know the color of this card. How much do you bet on this card? All of it. You bet all of it. You knew it was black. It is black. You've doubled your money. So you made 2% here. You could have lost 2%. Could have been black. And on the last card, you've doubled your money. How much money can you make gambling on this deck, assuming all 52 factorial permutations of the 52 cards are equally likely? Well, what is it? Blah, blah, blah. One way to see it is this. B star of x52 is P of x52. And balanced decks, if the summation of xi equals 26, then this probability is 1 over 52 choose 26 for x that satisfies this, and the probability of seeing a sequence of 52 cards that isn't balanced red and black is 0. But the odds, x52, when I multiply those out, are 2 to the 52. So the amount bet times the odds are S of x52 is B star x52 times odds of x52, which is equal to this number times this number, which is 9.18. If the deck is a fair deck. For all x such that it's a fair deck. So here's what you did. You just said, look, I know I can gamble sequentially 23 over 49, blah, blah, on red and black. But it amounts to the same thing as my saying, let me take my dollar and divide it into 2 to the 52 stacks. Some of the stacks will be empty. I won't bet anything on the unbalanced sequences. And I'll bet an equal amount. That is, because this was uniform, I'll bet a uniform amount on those that are left. So that I get 2 to the 52 for 1 odds. And only this many things can happen. And this ratio is 9.18. Great. How many bits are there in a string of 1s and 0s of length 52 of fair coin flips? Answer, 52. They're fair coin flips. But these aren't fair coin flips because of the dependence. They sum to 1. So how many bits are there here? The answer is, just take the logarithm of it. Log of 9 is 3 bits. Log of 8 is 3. So 3 bits. Instead of 52 bits of randomness in this sequence of red and black, there's only 49 bits. And indeed, that can be reflected in a data compression scheme, which will be the subject of what we talk about later and Thursday. So you can save 3 bits in describing such a sequence. Notice there's a nice minimax aspect here too. It says, I make this amount on every sequence. But let me show you what a roller coaster ride you can have. Here's n, 1, 2, through 52. And here's S sub n, the amount of wealth you had. Well, we started with $1, and at time 2, we had a little more than $1. And at the end, you're going to have $9.18. But let's suppose the first 26 cards were all red. So you'd be betting more on black each time because there are more black than reds remaining. You'd be losing every time. And eventually the 26 red cards would be gone and you would have lost a lot. But now you're in position to gain a lot. By the way, how much will you have lost? You will have dropped down at 26 to something like 9.18 over 2 to the $26. So your initial dollar will be very low, and if you're married, your spouse will be saying, "You've got to quit." But the point is, from there, they're all black. You know that. You're doubling your money every time. And by the way, that's how I figured this out. You multiply this by 2 to the 26, and 3 cards from the end, you go positive for the first time, and you end up with 9.18. So that's the roller coaster ride you can have. Sequences can do all sorts of things, but they all end up at 9.18. Okay, thank you for the cards here. I hope I didn't mess them up for you. All right. So the application 3, and then we'll take a break after that, is the entropy of English. Rate of English. This is not to S. All right, here's the past. You're deep in a novel. This novel turns out to be a work of nonfiction called Jefferson the Virginian, and it was used by Shannon to use a guessing game, which I've already slightly disparaged because of its round-off qualities. We'll use it to estimate the entropy of English. Well, we'll estimate it using gambling, which gives us a slightly better estimate. All right. This is not, they're both upper bounds, but this will be a lower upper bound. All right. So There's A through Z